Good afternoon, everybody. My name is João Ribeiro, and I'll be presenting you my work on damage model calibration and application for material S355 steel. Just a little bit about me. I come from Coimbra in Portugal, and obviously we are all in Catania. And why is this important? Why I need this? I come from the civil engineering department, and we are interested in improving structural robustness. And in the case of sudden column loss, the vertical loads will have to distribute themselves to the neighboring columns, and this will affect the joints immensely. They have to perform at elevated deformation levels while avoiding brittle failure. And so, if we go to the Eurocodes, we can establish the plastic resistance of the joint, but we cannot. Sorry, what is that? Oh, okay. So, we are losing all this part, this toughness part, and we cannot establish the joint ductility. So we could establish any failure criteria for this, use some experimental testing, or use some finite elements with a damage model to predict its ductility. Obviously, we are all aware of this strain constitutive relationship for steel, and obviously the elastic part concerns the elastic stiffness and the yielding stress. Then we come with hardening up to the ultimate tensile strength, and afterwards we have some softening. And obviously steel is a material with elevated toughness, and this compares it to a bolt grade 8.8, which has much less toughness. Alright, so obviously we want to connect all of this, a material model, robust as much as I can, and then evolve to connection studies and eventually study the robustness of full-scale structure. So again, the constitutive relationship of steel. Okay, without damage we have here the true stress relationship, and we here in this presentation aim to discuss this softening part. So within the continuum damage mechanics field, I think we are aware that a porous medium like steel, we aggregate in a continuum medium, okay? And we have a damage variable that simulates all this behavior, the void growth and coalitions of voids, which will eventually result in a crack. Alright, so the methodology for this work, we have some small scale experimental tests. We run a finite element model without damage properties, and then we reseeded the numerical models to get the triaxial stress state of the different specimens, and then we could get a triaxial dependency and manage to establish for the Johnson-Cook damage failure model, and then we run the analysis with the damage model and finite element deletion, and eventually we can predict the joint utility and evaluate structural robustness again. Okay, so these are our specimens. Okay, we'll be discussing these flat ones. We also have round ones, which will give us the deviatory state parameter equal to 1. We have both unnotched and notched specimens here, so that we could have different triaxial stress states. So these are pictures of the models of the experimental testing that occurred with a very low speed, in line with the static loading. And here, of course, we have the results, the strain stress results, and we can see as the notch size increases, that that the DCL plateau disappears, mostly because we cannot read the strain localization very accurately, and also that the ductility seems to be reduced, obviously because the strain localization gets higher as the notch increases. Okay, so here are the finite element models. We run a full 3D model because the specimens are so small, and we run it in an explicit solver with a slow velocity. And obviously we have input the true strain relationship, and this CL plateau, this plateau here is the assumption of the software where when it hasn't any more data, it will establish a plateau. So these are the results of the simulations, and we can see here that the simulations will continue past the fracture of the experimental tests. And this may lead to an engineering error. So we have received the analysis to check how the numerical models, what are the stress states there. Obviously you can see them here, okay? And here we have the plot for the equivalent plastic strain and the triaxial stress states. And afterwards we went to the Johnson-Cook failure model and calibrated the D1, D2, and D3, and we only used the first part of the equation. Okay, so we used this curve to establish the onset of damage, and we proceeded to compare again. These are the experimental tests. These are without damage, and obviously with damage we could get a failure and predict the failure a little bit better. And these are the final geometry of the specimens with finite element deletion technique. Okay, so for some conclusions, I've used the continuum damage mechanics to obtain the failure. And the experimental tests obviously have provided the triaxial stress state, and we could see that with the notch size the global ductility is reduced, straining gets more localized, and the cross-section straining also gets reduced. I just wanted to state some difficulties I had using this model, because the user is required to input the triaxial peak dependency at the onset of damage. Then we have to define damage evolution, which is affected by the finite element size. And eventually I got caught on this circle, but I don't think I've said, but I used a damage evolution of a linear damage evolution of with a plastic displacement of 0.1 millimeters. Okay, so I'll leave you some videos if they play. So we have the material, the connection, and eventually the structural analysis. Thank you very much.